Different terminologies used to describe the characteristics of instruments. Today, probably coming another 2 classes, we will be talking about this topic. There are a variety of terms, starting from accuracy, precision, repeatability, reproducibility, sensitivity, range, frequency response, resolution, least count, like that. Number of terms, more than 20 terms are there. Okay, so today and maybe another 2 to 3 classes, we'll be talking about various terms that are used to describe the characteristics of instruments. So that's the agenda for today and coming classes. Fine. Why we need to learn? Because as an engineer in a company, you need to buy equipments, okay, buy instruments, measuring instruments. While buying, you have to give your specification. See, I want to measure temperature with an accuracy of plus or minus 1 degree Celsius, plus or minus 0.5 degrees Celsius, plus or minus 5 degrees Celsius. All these are different instruments. The cost of the different accuracy instrument will be different. Plus or minus 5 degree accuracy instrument, you may get it for 100 rupees or even 200 rupees sometimes. Cost of plus or minus 0.5 degree accuracy, will same temperature only this also will measure, but accuracy is very small, plus or minus 0.5. But the cost will be maybe 5,000 rupees, 50,000 rupees, maybe 5 lakh rupees, we don't know. So as you change the specification, the cost of the instrument for measuring the same parameter increases very high. For example, scale, 3 rupees you will get plastic scale. Okay, what is the the length or to what level you will be able to measure? Maybe mm you will be able to measure, isn't it? Okay, mm also I am doubtful. Okay, so with an accuracy of mm you will be able to measure with a normal scale, but you will get it at 3 rupees, 5 rupees, maybe in the VAT mark, right? Whereas you go for little more better instrument. You will go for micrometer or vernier caliper, something like that, 0.01, 0.001 accuracy. You will get it somewhere around 5,000 rupees, 6,000 rupees, you will get gauges like that. Some more better instrument. So you have 0.001 you want to go, then you have to go for electron microscope or some other sophisticated instrument to measure the same distance, or the same width of the object or thickness of the object you want to measure. You have optical projector to measure that. That will be around 5 lakhs rupees. Electron microscope, maybe 15 lakhs rupees, something. As the specification is becoming tighter and tighter, the cost of the instrument goes high. Whatever it is, according to your application, you have to order the instrument. Okay, that's another point. One is the cost. Second one is the suitability of the measurement. Okay. So for measuring the size of the room, you will not buy an electron microscope or to measure this. There is a range that you have to measure. Vernier caliper also you will not use to measure the size of this room. So there is a range of instrument. There is an accuracy that is needed. For that, what is the right instrument that we should buy? We have to decide as an engineer. That's an engineer's job. And once we decide, then we have to communicate that to the manufacturer. They may be manufacturing variety of instruments. So as an engineer, to convey the specification to the manufacturer, the characteristics of instruments, understanding about the characteristics of instruments is very much important. Similarly, as a design engineer, one, we buy the already existing instruments, or as an R&D engineer, we will design our own instruments. That time we should know what are all the requirements for which we have to design our instruments. Then we have to design our instruments to meet our specifications. For both these cases, a thorough understanding of characteristics of instruments is important. Okay. Right. The first term in that characteristics is accuracy. Okay. Accuracy refers to the closeness of the measured value to the true value. Okay. There are 2 things. One is the measured value, the other one is true value. A lot of discussion we can have. In fact, in the past 5 to 6 years, when I handled this subject, only on accuracy I spent the entire class, 1 hour. Okay, I don't know whether we will be able to cover this class. So much we can talk about the sperm accuracy. Okay. So there is something called true value. There is something called measured value. Okay. What is meant by measured value? That's very easy to understand. You have an instrument you bought from the market. You go connect it to the parameter. For example, let's say we have a temperature measuring device, thermocouple, for example. A thermocouple is a temperature measuring device. You are aware of it? Okay, fine. So that's a temperature measuring instrument I bought. I went and the sensor part I put it inside the hot medium, and I'm trying to measure the temperature. Some reading is shown on the gauge. That is the reading or the measured value. That is the measured value. Then what is true value? True value is the actual temperature of that medium. Okay, the actual temperature of that medium. Is it understandable? Okay, fine. So measured value is what we perceive, what we measure through the sensor that we have or the instrument that we have, and the true value is the actual value of that medium. Okay, and the great problem comes in getting the true value. Great problem comes in getting the true value, because most of the time it's very difficult to get the true value. Any instrument that we use, it will show its reading. Any instrument that you will use, it will show its own reading. We never know what is the actual temperature. For instance, temperature I have taken purposefully because it makes our job easier in explaining the true value. At least I can have two different values of temperature. For example, I take water. Two values I can fix. One is the freezing point of water, other one is boiling point of water. What is the boiling point of water? 100 degrees Celsius, isn't it? In a very controlled environment, people have conducted experiment and proved that 100 degrees Celsius water boils. Okay. In fact, it is the other way around. The temperature at which the water boils, they defined it as 100 degrees Celsius. And the temperature at which the water becomes ice is 0 degrees Celsius. Okay. So we know these two temperatures. So any device that I have, I can take that as a true value, make the water to boil and measure the temperature. And true value at that condition is 100 degrees Celsius, and whatever the reading I get will become the reading. So reading and true value I will be able to get here. And there is something called reference value. Okay. So the formula for calculating the accuracy is true value minus reading will give you the error, isn't it? True value is the actual temperature. The reading I am getting is, the instrument is something different from that. Actual value, something different from that, will give you the error in the measurement, isn't it? It will give you error in the measurement. So that error divided by some reference value into 100 will give you the accuracy. That's the formula. Okay. So the meaning of accuracy is the closeness of the measured value to the true value. Closeness of the measured value to the true value. If it is very close, that means it is very good, accurate instrument. If it is, the measured value is far away from the true value, then the accuracy is less. Is that clear? That's one. Number two, at this point, you have to understand, when we say accuracy, it's the English term accuracy. Actually, we mean inaccuracy in the instrument. It's very important to understand. We actually mean inaccuracy in the instrument. Actually, the terminology should be inaccuracy. Then the verbal meaning and the technical meaning will coincide. We say accuracy, but actually we mean inaccuracy. Let's say we have plus or minus 2% instrument, plus or minus 5% instrument. Okay. Which one will have better reading? Which one will have less error? Plus or minus 2. Okay. But accuracy, what is the English meaning of accuracy? Very accurate. Means what? Very accurate means the better the number, the better the instrument should be, isn't it? This is just 2% accuracy. This is 5% accuracy. So according to the verbal meaning, this should be the 5% should be the good instrument that we should choose. But actually we don't convey accuracy as accuracy. When we say accuracy, that's a technical term, we mean inaccuracy. So wherever inaccuracy is smaller in number, that's a better instrument. Okay. So by the term accuracy, we mean inaccuracy. So whenever accuracy, you see some number, plus or minus. Plus or minus is there. We'll explain why, what, and what does it mean, and all the terminologies. 2-3 slides are talking about that. And this is not the final formula. We are going to give a little more refinement to it. This is a crude theoretical explanation of accuracy formula. Okay. So 2 points. One is the definition. The measured value, how close it is to the true value, is the accuracy. That's how we define. And what we convey through the term accuracy is inaccuracy. That means smaller the number, better the instrument. If accuracy is plus or minus 0.1, plus or minus 1. 0.1 is smaller, so that will be the better instrument. Clear all of that? Right. Now, we discussed all the components involved in the formula and try to understand it better. I talked about reading, whatever our instrument shows is the reading, and true value is the actual temperature being measured. How do we get the actual value? It is not that always we are going to measure water temperature, so 100 degree and 0 degree are there. Okay. Sometimes we may be measuring length, sometimes we may be measuring velocity, sometimes we may be measuring pressure. Okay, so we should have some standard. We should be able to measure the actual value we should be able to get. Getting an actual temperature, actual value is the tedious job. For example, I want to find out the length of this. Okay. I have a device which will measure the width of this. Okay. And I get the reading. There is no problem in getting the reading. But how do you get the actual length of this rod? Or still, yeah, okay, fine. Probably if you use an inch tape, right, the normal measuring tape, and then measure. What is the value that you will be able to get? Maybe something like my measuring instrument I use, and then I don't name it, X instrument, 30, 60, somewhere around 65 mm. Example, just for an example, orbit, 65 mm. Okay, so 65 mm is the reading given by the measuring instrument. That's the reading is over, no problem. I got the reading. Now, I want to know, because that instrument will give you only mm, 65.00 mm, my instrument gave, reading is over. What is the true value of this? I take an inch tape, measuring tape, measure it, that also shows 65 mm. 65 mm. Then, I take a vernier caliper, and then measure, I get 65.57 mm, some 2 digits. 57, yeah. I take such a big micrometer, maybe you make special design and I do an extra attachment so that such a long you will be able to measure. You measure the same width of this length, you will get 65.57, maybe 2, 3, one more digit you will get. 65.574. Some number you will get. Third digit also you will get. You understand? Better the instrument we measure, the next digits we will be able to discover. Next digit we will be able to discover. Does it mean the better instrument I use, the length of the object keep on increasing? Earlier it was only 65 mm. Now better instrument 65.57, 65.574. Is the length of the object increasing? No. We just discover the next digit of the true value using a better instrument. You are able to appreciate that? Right? So, with any instrument, will I be able to get the true value? With any instrument. Let's imagine this, the most sophisticated instrument that we can think of. Will we be able to measure the actual length of this particular object? No. There are, after decimal point, there are infinite number of digits, and we will be able to discover only few number of digits. So, in reality, any parameter for that matter, let us say temperature, pressure, length, velocity, any physical parameter that you name it, measuring the true value is impossible. Is impossible. We lose all our hopes. Then what are we doing then? We call it as instrumentation, a lot of instruments, and then we measure. Okay. Then we come for a compromise. Okay. Okay man, come on. Anyway, I cannot measure true value, and without true value, I cannot measure. I cannot find accuracy. Without true value, I do not know what is a reference and all that. True value is important for entire measurement. So we need to come to a compromise. So we come and then say, hey, I'm doing a carpentry job. I'm doing a carpentry job, right? And for that, if I get mm level accuracy, 65 mm, point dot dot dot, anything, it's okay. I'm able to make good carpentry work. So that my chairs are perfect, I'm able to sit. The function of the carpentry products are servicing, no problem. Okay? They are pakka. You go to automobile components, 0.00, that means .xx. 2 digits of information if I get after decimal point. Most of the automobile components, the fans, the cycles, the bikes, cars, those kind of components, any engineering components, household engineering components, I'm able to do it with either 2 digits of data after the decimal point or 3 digits of data. For more sophisticated engineering, you go to maybe aerospace engineering or even still precision engineering, I mean at 4 digits after decimal point or 5 digits after decimal point. I'm able to do the function of what is it intended for. The components used in aerospace, I'm able to do its function. If I'm able to manufacture components, measure the components dimensions to 4 digits accuracy or 5 digits accuracy. Fine. Then I strike a compromise with this world. I say if I'm able to measure up to 4 digits, 5 digits, I'm okay with it. So having come to that compromise, and then we say hereafter we say this is true value for this kind of applications. Okay, we know it is not true value. Theoretically speaking, it is not true value. But then we strike a balance. Okay, for this will be the true value. So true value or the actual value is is a mystery, undiscovered truth. But we come to a compromise and then say for these kind of applications we say this is true value. Okay man, come on. Hereafter we call this as true value. There is no ideal leader in India. But then whoever we have hereafter, okay, for this fellow will be the leader for us. For Tamil Nadu, no big leader. So then there is no leader at all. We dissolve all systems. No. We say, okay, out of available people, this fellow is free and this fellow is reasonably good, so we will make him a leader. Okay. Okay, this fellow does all necessary functions, even though he screws some money. That's okay. Fine, we will take him as a leader. We compromise. That is the level of compromise we made on measurement. And then we say, for a type of measurement, we said this will be acceptable as a true value. So such a value will become true value. In theory, idea-wise, and in practical. In practice, you take any instrument, for example, if 1 decimal point is the accuracy that you are expecting in the instrument for taking reading, while calculating accuracy, you should take 2 decimal point accuracy instrument as a reference value, at least. Okay? That means if the instrument I am calibrating, finding the accuracy for 10.3 mm, that means that output will be 0.1, 1 decimal point accuracy. My true value instrument should give 2 decimal point accuracy, 10.32, 10.35, something. The second digit, 2 decimal point accuracy the instrument should give. Such an instrument, whatever the reading gives, we know it is not true value. That also will have some error. But we call that reading as, that's a reference instrument. We call it as a reference instrument. That reading as what? True value. We know it is not true value. Okay, that is what I have been talking about. But we will say, and then this hereafter it will be true value. So true value is undiscovered. We strike a compromise, and then we call 1 decimal point more item as true value. Okay. So you understand what is meant by true value in the formula, accuracy. Okay, fine. Now reference value. In the denominator there is a reference value. Okay. Error. Sometimes no. When you measure 1 degree Celsius, the reading might have shown 1.3. If you measure 100 degrees Celsius, 100.3 is small percentage of error. 1 degree Celsius, same 0.3 is 30% error. I mean, huge error. So we wanted to normalize this. We want to normalize this and then come out with a number which represents a number which tells in its inability to show the actual reading. Okay. For that, what we did, the error divided by the reference value into 100, so that the percentage of that value we will be able to get. You come next class, please. I'm talking about you, yeah. You'll meet next class. Okay, somebody falls asleep because they are not out of yesterday's travel or tired, but intentionally somebody is sleeping. I warned him, but then he didn't take that point. That time itself he was trying to sleep. That's the first warning for the entire class. And subsequently, if such things are happening, permanently we will send him out of the class. I told you in the very first class, if you are not able to actively participate in the discussion, please don't come to a class. Okay, fine. So, reference value is for normalizing this value. We have an error, whether it is for 1 degree, whether it is for 100 degree, we should give a number which is applicable for all this. So, percentage of error, they wanted to calculate. So, percentage of error is actually a different technical term. I will come to that. Before that, so they wanted to have a accuracy for the entire range. So they divide the error, divide by the reference value. Okay, into 100, of course. Okay. So the formula for accuracy will have the error term on the numerator and the reference value in the denominator. The reference value can be either the true value that we have been talking about, true value, or it can be full scale deflection. It can be full scale deflection. FSD they call it. Full scale deflection. FSD. What is meant by full scale deflection? Suppose an instrument can measure up to 50 degrees Celsius. When the needle of the earlier, most of the instruments were needle type. So that's why it is full scale deflection. By deflection only, the readings were taken. When it is fully deflected, what is the reading that it shows? That is full scale deflection. That means, what is the maximum value that you can measure using that instrument is full scale deflection. That value you can use in the denominator, or the so-called true value we have been discussing, that you can use it in the denominator. Out of these two, you have to choose one. If you are a manufacturer of the instrument, which one you will use? Is it the true value or the full scale deflection? This is the formula as of now. Of course, we are going to refine it. As of now, this is the formula. Okay. Let's say 0 to 250 degrees Celsius is the capacity of the instrument. I may measure 50 degree, I may measure 100 degree, I may measure 150 degree. So our true value will be slightly smaller than the full scale deflection, isn't it? Full scale deflection is always 250 degrees Celsius for that instrument. So I have an instrument, I am the manufacturer of that instrument. I have to calculate accuracy and then sell it in the market. Which is advantageous when people will feel better about my instrument if plus or minus 0.1, 0.2 like that, smaller number is better or bigger number is better when I am selling it in the market? Smaller. So if you are a manufacturer, will you suggest full scale deflection or true value? We have two choices. As a reference value, which one you will choose? Full scale deflection. Why? That's the bigger number in the denominator leading to smaller number for the accuracy. So it looks as if it is a better instrument. The moment I see, oh, plus or minus 0.2. Whereas if for the same instrument, for same reading, you take true value as a reference value, it will have slightly a bigger number in the accuracy term. So people will think, oh, it is not so accurate. Okay. But that's the first glance and then use the first impression. It is mandatory that you should put whatever is the reference value you have used in the brackets. Specifically, if you have used full scale deflection, you have to put it in the brackets full scale deflection plus or minus 0.1% FSD or full scale deflection. It is mandatory that you have to give. But some manufacturers cheat the people there. They won't put, but they used to calculate like this. If it is not put like that, you have to understand those people have used true value as the reference value. You have to assume. It's only an assumption. With the understanding, it is mandatory to put FSD if they have used FSD. Okay. Technically speaking, both are correct. Sir, I have computed accuracy using true value. Sir, I have used accuracy using full scale deflection. Both are technically correct. Both are technically correct. So as a manufacturer, I prefer to use FSD because that gives a smaller. I have two choices. One is true value, other one is full scale deflection. Okay. Now tell me, you understand what is mean by accuracy? Okay. You understand the terms involved? Yes or no? True value, reading and reference value. Correct? Clear? Right? Now, I want to compute accuracy. I want to compute accuracy. I am the manufacturer. Number one, about computing you have to understand is accuracy is not calculated by the users. Accuracy is not calculated by the users. The manufacturers compute it and print it as part of the catalog or the advertising material or product specification page they will keep and then give you. So accuracy is always at the manufacturer's side. So they manufacture instruments, they compute the accuracy and then they sell it. Okay. We only, if at all we need, we verify by using. Okay. Is that understandable? Yeah. Now, I have an instrument, I have to calculate accuracy. So what do? I take, let's take the thermocouple example itself because that we are familiar, isn't it? So we take thermocouple, we have a hot bath. I have one better device which will show you the reading one decimal point more than the thermocouple. Let's say thermocouple will give you 2 degrees, 2 decimal points of temperature. That means, let's say 70.73 degrees Celsius, something like that. I will have one more reference temperature measuring instrument, maybe some other type, which I call it as reference meter, which will give you 3 digits of information. Okay, 3 digits of information. So that's the reference value, and then I measure the reference value. Reference value, that means true value. Okay, true value I will measure. Let us say now it is 70.33 something. Okay, 70.33 is the true value. My instrument I put, it will show 71.2 degrees Celsius. Some far away from the so-called true value. Okay, so you have true value, you have reading, and the instrument which is getting calibrated, whose accuracy we are computing, that full range, let us say 250 degrees Celsius. So the difference between those two divided by 250 into 100 will give you one accuracy. Will give you one accuracy. Okay. That is also accuracy only. That is also accuracy only. But that is the accuracy at that particular temperature, at 70 degrees Celsius. At 70 degrees Celsius, for example. But we should give accuracy for entire range from 0 to 250 is the range of measurement for that device. We should give for 250 degrees Celsius, we should give one number as accuracy. We should not give only one measurement randomly we take and then we give that. Okay. So what we should do is we should conduct multiple experiments at various temperatures starting from 0 degree, 5 degree, 10 degree, 50 degree, 100 degree, 250, 240, all equally spaced temperatures we take reading. Correspondingly, you take the true value and the measured value, compute accuracy. Every reading that you compute, there is no guarantee you get the same accuracy. There will be some smaller number, there will be some bigger number. It's a mix of numbers you will get. Okay, let's say 0.1% accuracy, 0.1.2, I mean, not 0.1.2, plus or minus 1.2, plus or minus 1, plus or minus 0.9, like that. A variety of numbers you will get in and around. Out of that, whatever is the maximum number, that will be the accuracy for that instrument. That will be the accuracy for that instrument. So accuracy in companies, they calculate, they take multiple readings, take the maximum value of that error. Actually, what we mean by accuracy, accuracy is how close your reading will be to the true value. Okay, that's the maximum error that the instrument can produce. In other terms, accuracy is the maximum error the instrument can produce. Let's say if I say plus or minus 1% of full scale deflection, 250 degrees Celsius is full scale deflection in the example that we have taken. 1% of full scale deflection is what? 2.5. Suppose if I measure 70 degrees Celsius, my error can be plus or minus 2.5 degrees Celsius. 1% error. That means actual temperature using my instrument I am getting 70 degrees Celsius, 70.00 my instrument shows. But what is the actual temperature of the instrument? It can be anything between 72.5 on left hand side, 67.5. So any temperature between 67.5 to 72.5 may be the actual temperature. My instrument will show 70. Okay, it may be 70 also. Very coincidentally, it can be 70, exactly 70 degree also, but there is no guarantee. All we can say is the temperature of the bath is definitely between 67.5 and 72.5. That much you can get. If it is 0.5% accuracy, then you can still narrow down the range of your actual temperature. Narrow down. Okay. That is why accuracy is important, very prime term that you should use, and that tells what is the maximum amount of error your instrument will make. What is the maximum amount of error your instrument will make is accuracy. But don't write this as a definition for accuracy. That's your understanding. The definition is accuracy is the term which tells how close your readings are to the true value. Okay, so let's see. I think we have learned the meaning of accuracy, the formula for accuracy, the terminologies involved, how to compute taking multiple readings. Very important. There is no question paper without characteristics of instruments in both CAT 1 and in the final assessment. Eventually, many times I ask this question, people make mistakes in taking multiple reading and take the highest value. students normally make mistakes. They know how to compute accuracy. They know how to put values in the formula and then compute. They fail to understand the maximum value. See, true value minus reading, it's a modulus value, and then max. Why I put modulus value? Because error can be on the positive side or error can be on the negative side. Anyway, there is a plus or minus. So absolute error I am taking. I am not taking the individual value. Maximum of that error divided by reference value into 100. So you should take the maximum error. You should not take any in between. There students make mistake. Very important. And plus or minus we put because my instrument says some value. The error can be this side, error can be this side. Okay? So my actual value, the true value can be lower than my indicated value, higher than my indicated value. That is why the plus or minus sign is given. Modulus is given because the absolute error I am taking for calculation purpose into 100. Max is given because maximum error produced by the instrument we are taking. So that's that. And one last but very important term. That's the pointer for the next day's class is accuracy is the term attached to the instrument. It is the property of the instrument. It is something like a bowler will have a rating, a batsman will have a rating that is attached to him. For example, Dhoni, his batting, the strike rate is, let's say, 125 or something like that. Is the number attached to Dhoni, not that day's play. That day he might play very well, or that day he will come as a dugout without scoring anything. It is the characteristics of that player. Like that instrument, accuracy is attached to the instrument. That's very important. You may not catch the point fully, but remember this sentence. We will take forward from this point in the